Hello students. Welcome to Varun tutorials. In this video, we are going to learn equations reducible to exact equations. First, we will understand what an integrating factor is and how a non-exact differential equation can be converted into an exact equation. Then, we will study method 1, finding integrating factors by inspection using 10 important standard differentials. Finally, we will solve 5 examples step by step. First, let's explore equations reducible to exact equations. First, let's understand what an integrating factor is. Let Mdx plus Ndy equals 0 be not an exact differential equation. If the equation can be made exact by multiplying it with a suitable non-zero factor, u of x, y, then this factor, u of x, y, is called an integrating factor. Let us understand this concept with a standard example. Consider the differential equation, y dx minus x dy equals 0. Let this be equation 1. Here, m is y and n is minus x. Differentiating them partially gives, the partial of m with respect to y is 1, and the partial of n with respect to x is minus 1. Since these partial derivatives are not equal, equation 1 is not an exact differential equation. Now, let's multiply both sides of equation 1 by the factor 1 over x squared. This gives us the modified equation, y over x squared dx, minus 1 over x dy, equals 0. Let this be equation 2. Here, the new m is y over x squared, and the new n is minus 1 over x. The partial derivative of m with respect to y, and the partial derivative of n with respect to x, are both equal to 1 over x squared. Since the partial derivatives are now equal, equation 2 is indeed an exact differential equation. Hence, 1 over x squared is an integrating factor of our original equation. Let's look at an important note regarding integrating factors. Recall that the differential of x over y is equal to y dx minus x dy, over y squared. Also, the differential of log of x over y is equal to y dx minus x dy, over xy. And the differential of inverse tangent of x over y is equal to y dx minus x dy, over x squared plus y squared. Therefore, the functions 1 over y squared, 1 over xy, and 1 over x squared plus y squared are also integrating factors of y dx minus x dy equals 0. From this example, we observe that a differential equation can have more than one integrating factor. Now let's discuss the methods to find integrating factors of Mdx plus Ndy equals 0. Method 1, with some experience, integrating factors can be found by inspection. For this purpose, the student should keep in mind the following 10 standard differentials. First, the differential of x times y is equal to x dy plus y dx. Second, the differential of the quantity x squared plus y squared over 2 is equal to x dx plus y dy. Third, the differential of y over x is equal to x dy minus y dx, all over x squared. Fourth, the differential of x over y is equal to y dx minus x dy, all over y squared. Fifth, the differential of log of y over x is equal to x dy minus y dx, all over xy. Sixth, the differential of log of x over y is equal to y dx minus x dy, all over xy. Seventh, the differential of inverse tangent of y over x is equal to x dy minus y dx, all over x squared plus y squared. Eighth, the differential of inverse tangent of x over y is equal to y dx minus x dy, all over x squared plus y squared. Ninth, the differential of log of xy is equal to y dx plus x dy, all over xy. And 10th, the differential of log of the quantity x squared plus y squared is equal to 2 times the quantity x dx plus y dy, over x squared plus y squared. Let's solve the first question. X dy minus y dx, plus a times the quantity x squared plus y squared dx, equals 0. We start with the given differential equation. The equation is x dy minus y dx, plus a times the quantity x squared plus y squared dx, equals 0. To group the terms x dy minus y dx, we divide the entire equation by x squared plus y squared. This gives the fraction x dy minus y dx over x squared plus y squared, plus a dx, equals 0. Let's recall the related differential formula from our inspection rules. The differential of inverse tangent of y over x is exactly equal to x dy minus y dx, over x squared plus y squared. Now we substitute this differential back into our equation. This simplifies the equation beautifully to, the differential of inverse tangent of y over x, plus a dx, equals 0. Next, we integrate both sides of the equation. Integrating gives, the integral of the differential of inverse tangent of y over x, plus a times the integral of dx, equals c. Evaluating the integrals, we get the final general solution, inverse tangent of y over x, plus ax, equals c. Let's solve the second question. X dx plus y dy equals the fraction x dy minus y dx, over x squared plus y squared. We start with the given differential equation. The equation is x dx plus y dy, equals the fraction x dy minus y dx, over x squared plus y squared. Let's recall the relevant differential formulas from our inspection method. First, the sum x dx plus y dy can be rewritten as the differential of the quantity x squared plus y squared, over 2. Second, the right side is the differential of inverse tangent of y over x. Now, we substitute these two expressions back into equation 1. This gives us, the differential of the quantity x squared plus y squared over 2, equals the differential of inverse tangent of y over x. Next, we integrate both sides of the equation. This gives the integral of the differential on both sides, plus a constant of integration c1. Integrating both sides yields x squared plus y squared over 2, equals inverse tangent of y over x, plus c1. Finally, we multiply the entire equation by 2 to simplify it, defining c as 2 times c1. We obtain the final required general solution x squared plus y squared, equals 2 times inverse tangent of y over x, plus c. Let's solve the third question, y dx minus x dy, equals a times the quantity x squared plus y squared dx. We start with the given differential equation. The equation is, y dx minus x dy, equals a times the quantity x squared plus y squared dx. To group the terms on the left, we divide both sides of the equation by x squared plus y squared. This yields, the fraction y dx minus x dy, over x squared plus y squared, equals a dx. Let's recall the relevant differential formula for this fraction. The differential of inverse tangent of x over y is equal to y dx minus x dy, over x squared plus y squared. Now we substitute this differential into equation 2. This simplifies the equation to, the differential of inverse tangent of x over y, equals a dx. Next, we integrate both sides of the equation. Integrating both sides yields, the integral of the differential of inverse tangent of x over y, equals a times the integral of dx, plus c. This gives our final general solution, inverse tangent of x over y, equals ax plus c. Let's solve the fourth question. X dy minus y dx, equals x times y squared dx. We start with the given differential equation. The equation is x dy minus y dx, equals x times y squared dx. First, we divide both sides of the equation by y². This gives, the fraction x dy minus y dx over y² equals the fraction xy² dx over y². Now, we cancel the common term of y² from the numerator and denominator on the right side. This simplifies the equation to, the fraction x dy minus y dx over y² equals x dx. Next, we rearrange this equation by bringing the fraction to the other side. We write x dx minus the fraction x dy minus y dx over y² equals 0, which simplifies to x dx, plus the fraction y dx minus x dy over y² equals 0. Let's recall the standard differential quotient rule from our inspection formulas. The differential of x over y is equal to the fraction y dx minus x dy over y². Now, we substitute this differential expression into our equation. This simplifies the equation to x dx, plus the differential of x over y, equals 0. Next, we integrate both sides of the equation. This gives, the integral of x dx, plus the integral of the differential of x over y, equals c. Evaluating the integrals, we get the final general solution x² over 2, plus x over y, equals c. Let's solve the fifth question, the fraction y times the quantity xy plus e to the x dx, minus e to the x dy, all over y² equals 0. We start with the given differential equation. The equation is, the fraction y times the quantity xy plus e to the x dx, minus e to the x dy, all over y² equals 0. Let's expand the terms in the numerator first. This gives, the fraction xy² plus y e to the x, dx, minus e to the x dy, all over y² equals 0. Next, we split this fraction into two separate terms. This gives xy² dx over y², plus the fraction y e to the x dx minus e to the x dy over y² equals 0. We simplify the first term by cancelling out the common factor of y². This simplifies the equation to x dx, plus the fraction y e to the x dx minus e to the x dy over y² equals 0. Let's recall the quotient differential rule for exponential functions. The differential of e to the x over y is equal to y times e to the x dx, minus e to the x dy, all over y². We substitute this differential back into equation 2. The equation simplifies beautifully to x dx, plus the differential of e to the x over y, equals 0. Now we integrate both sides of the equation. Integrating term by term yields, the integral of x dx, plus the integral of the differential of e to the x over y, equals c. Evaluating these integrals, we get the final general solution x² over 2, plus e to the x over y, equals c. Thank you for watching. If you found this helpful, please like, share, and subscribe to Varun tutorials. Turn on notifications so you never miss a new video.